Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel where we talk about everything I want to, science and math. And today we're on physical science, learning about wave, sound, and light. So let's go through it. Let's do it. Except my notes are underneath the camera here. Okay, so we're going to talk about waves, and there's two types. They're sound and they're light, and they're different. So the first type of wave is called a compression wave. Okay, compression. So you can think about, have you ever had a slinky and stretched it out and then gone like this? And it makes little close places go down and back again. Have you ever done that? If not, don't worry, we'll be doing it in lab this week, okay? So that's a compression wave. So like these are where the rings are close, and there they're spread out. This is a slinky. If y'all know what that is, it's a springy toy, okay? And an example of this would be sound waves. Sound waves. And waves are made by energy. Like Alexa said, energy. Made by energy. So if I did this on a slinky, how often these compressions come by are called the frequency. The frequency. And it's the units of it is hertz. Have you ever heard of that unit before? Hertz, something in hertz. Hertz, okay. Okay, the other kind of wave is called a transverse wave. A transverse wave, and that's the kind of waves you think about like this. Ocean waves, ones like that. And we're going to learn some parts of this wave. And so tomorrow for your digital day, the two worksheets over there are your digital day assignment. I've scanned them, I put them on Canvas, but you can just pick them up and we should finish the notes early and you'll have time to work on them in class today. And one of the things on the worksheet is you have to label the parts of a transverse wave. Okay, so this little top part of the wave is called the crest. The bottom part where it goes down is called a trough. If you measure from crest to crest or trough to trough, you get the wavelength. I'm doing so much better. I'm writing so much neater than I did first period. I guess because we're on YouTube. All right, so the wavelength. And the fun thing about this is the symbol for wavelength is another Greek letter. It looks like a little upside down Y or a TP with something sticking out of it. So the wavelength is from crest to crest or trough to trough, and it's the Greek letter lambda. Lambda, lowercase lambda. Don't you feel smart learning Greek? It always makes you feel smart. How tall a wave is called the amplitude. The amplitude measured in amps. And there's an equation, wavelength, for wavelength that we'll talk about a little bit later. I don't really want to go over it right now. Can I scroll up? Yes, sir? No. You can go sit in Jonathan's seat, but don't talk. All right. How about to there? Can we go to there? Yes. Okay. Now, waves can bounce back, and that's called reflected. I bet you already knew that. They can be reflected, or they can change directions, and that's called refracted. Reflected or refracted. They can spread out, diffused, or they can be added or subtracted, and that is called interference. They can have interference. Okay, how do we feel about waves so far? Pretty good? One day I was getting a little too creative with my stampers, but I realized, look at this, that I've lost these stampers. I don't think I have the bird anymore, the car, that little rat fellow, or whatever I made the pier out of. So anyway, this unit was the first one where I made doodle notes. And this was when I very first started experimenting with this a long time ago. And originally I saw that's why it's all handwritten, where now I type them. Okay, so now I go to the next page? Mm-hmm. Yes? Anybody need to stay? It looks like you're still writing. Okay, we can wait. Did y'all ever learn this before in like middle school or anything? Have you ever learned the parts of a wave before? I knew first period seemed to already know all this. I loved it. We went so fast. Now can I scroll?
Yes.
Okay. All right, page number 2. Let's talk about sound. Okay. Things that stop sound are insulators. And a lot of times things that stop sound also stop heat because they have air pockets in it. So it stops that energy. Now, this is a tough question. Which one do you think can transmit sound fastest, solid, liquid, or gas? You would think it would be gas, but it's not. It's solid. Solid. And I'll show you where you might have noticed it before. Okay, so first of all, let's talk about how that liquid transmits better than gas. Have you ever been swimming in a lake and had your head above the water and all you hear is quiet? You hear birds and it's totally quiet, but you go under the water and you can hear a boat. You go back up, you can't hear the boat. It's because the boat sound is going better through the water than it does through the air. If you've ever seen old movies where it's a Native American or a cowboy and they're there and they're listening for a train and they can't hear the train through the air, they would put their head down on the railroad tracks and they could hear it through the tracks. Has anybody ever noticed that you hear better through a solid? Putting your ear up to a door, you hear better through the door than like a couple of inches off the door trying to hear into the other room. Not that you should do that. Okay, so how high the sound is called the pitch. Okay, and it's related to the length of what's vibrating. So I'm going to say it's related to wavelength. It's whatever it is that's vibrating, making that sound. Do y'all already know the units of sound? Starts with a D. Decibel, yes. Decibel. Okay. So you can make sound louder, and it's called amplify. To amplify. So anybody ever used a megaphone like cheerleaders and yelled into them? They really make it louder. They squish the sound together and make it louder. Yes, Luis?
Can I go through it?
What?
Can I go through it?
After we get through the notes. Not now. I don't want you to miss anything. Okay, because you can't hear me from the restroom. Oops, I made it small. See if I can make it big again. All right, so to amplify is to make it louder. Now, this is sort of a funny definition in physics. The definition of unwanted sound, what we call it, is noise. And it depends on your opinion. Like, you might think rap music is great music, but your mom might think it is noise. You might think something is nice to hear, someone else might think it's noise. So it's up to your opinion. So that's kind of funny. There's something in physics that's on just your opinion. Okay, so music is part of sound, and it's based on the octave. What number is the octave? It is 8. Oct means 8, right, Luis? Take out your earbuds, please. I want you to listen to the notes. Take out off the other one, too. Take them all down. Remember, no phones. You got to have a phone making that in music, and you're not supposed to have your phone. Phone in the book bag in the cubby. I'll watch you go put it away.
Damn.
I'm serious. I want y'all to pass. Let's have the pass speech again. This class is needed for graduation. All you need to pass this class is just show up every day and do what I want you to do. After that, you'll pass. It's not hard if you just do what I want you to do. Okay, the next thing is this. It's called the Doppler effect.
Wait, that is 0
What?
on base or octave?
Octave is 8. It's the number 8.
8?
8. The Doppler effect. Now, we already learned about this in a video we watched. It was the one about the figuring out about why everything's in hydrogen out in the universe. And so what the Doppler effect is that you can tell if something's moving towards you or away from you based on this. And this is how it works. Here I've got a train that's making noise. And when it makes noise, the sound coming toward you gets compressed because the train's moving forward. It's moving forward into the space where the sound is. Does that make sense? But behind you, the sound spreads out because it's getting left behind as the train moves forward. So that's you with your big ears listening to it. And when you listen to something coming, it sounds a higher pitch. But when it's leaving, the sound's spread out and it sounds like a lower pitch. Where I always think about this as motorcycles. Here comes a motorcycle. But when it passes me, it sounds lower. You hear it with sirens. Woo, 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 woo. And remember in the video, it was the guy with the white shorts on, the very un-in-style shorts, and he had the can and he was swinging around. And remember they explained Doppler effect is it's a shift in pitch, and it works for sound and light. And so in the video, we saw that they could tell if planets or galaxies or stars are moving toward us or away from us based on the Doppler effect. Okay, do you remember that a little bit in the video? The pitch thing? Okay. So it's used to predict motion if something's moving towards you or away from you. So it's also used like to predict tornadoes because tornadoes rotate and they can see that motion of it going towards you or away from you, and they know you've got rotation and you've got a tornado. Anybody ever seen a tornado in real life? I did once. It was pretty interesting, but a little scary. It was the one that hit Dallas a few years ago. Okay, can I scroll this up? Everybody got it?
Motion.
Last thing is motion. It's used to predict if something's moving motion towards you or away from you. So like tornadoes. Okay, now we're going to talk about light. Boom. We're through what? We're through waves, sound, and now we're to light. The light's got a little bit more. Okay? So we're already to the next page. Okay, so there's 3 ways that light can go through something. The first one is transparent. Transparent. Most of the light is transmitted like that window. That window right over there is transparent. You can see through it. What is it called when no light goes through? It starts with the O. Do y'all know? It's called opaque. Opaque. So my water bottle sitting right there is opaque. You cannot see through it at all. No light going through it. But if a little light goes through, what's that called? Starts with the T. I think someone whispered it. Translucent. Do you know that word? That means you can see through it a little bit, like a frosted glass pane or something. Might have that in your bathroom where people can't really see into your bathroom. Some light passes through. Okay, next we're going to talk about reflecting light. We're going to talk about mirrors. Can I go up?
No.
How about if I go up to there? Okay, so mirrors make an image. It's what you see. I bet you already knew that, your image in the mirror. How mirrors work is they are smooth, not rough. So the light bounces back so orderly that you can see it. Over here is concrete. And Alexa cannot see herself in this concrete. because the light hitting it is being bounced off in all different directions. But the smoother something is, the more you can see yourself in it. So like this board, I can actually see it a little bit. I can see the lights up there really well. I can see a little bit I can see the door. I can see the flag. I can read the posters actually right down there because it's smooth. But if it's a mirror, then it's so smooth it's glass, and it's got metal on the back that's very, very smooth, and it has your image going back. Now, when the light comes in and bounces off a mirror, they have names for it. Here I have a flashlight shining down on a mirror and bouncing off. And the light coming in is called the incident ray. You know how light can be called a ray, a beam of light, a sunbeam, a sun ray? So it's called the incident ray. The incident ray is the light coming in. So draw an arrow down to the flashlight. The light that bounces off is called the reflected ray. The reflected ray, okay? And there is a perpendicular line. Do you remember geometry class? The little square is perpendicular. There's a perpendicular line going up, imaginary, called the normal. I don't know why it's called a normal. Seems like a dumb name to me, but that's what it's called. Okay, and then if you measure the angle of incident, if you measure the incident from the incident ray to the normal, that is called the angle of incidence. If you measure from the normal to the light that's bouncing off, it's called the angle of reflection. And if you go on to take the other physics class, Luis, I want to see, I'm going to just sit here and watch. Let's see you put your phone away. You faked it before. I saw you do it. So now you're interrupting my class.
I didn't interrupt.
Yeah, put it away in your book bag and put your book bag in your cubby. We're going to wait on you to do it. We can play the Jeopardy music while we do. Dun 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 dun. Dun 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 dun. Put your earbuds in the book bag too. That way you'll hear everything and you'll do great on this test. Okay, I don't want to see them anymore. No, I want you to listen to me, not to whatever you're listening to. Okay? Nope. No. If you can't do it, I can write you up. I don't want to write you up. Just do it. Put your stuff away. This is day one rules, day one. Put them away. Turn around so I can see you put them in, Luis. I want to see them go in. I need to watch it happen. Okay, now I want to see you. Nope, turn around toward me. I want to see you zip it up. Is it there? You swear? All right. All right, now we can get on back with class. Unless y'all want some more of my sweet singing. Okay, so here's the concrete. It's a rough surface. It's not going to reflect an image. And the reason why is because it's rough. Okay, for mirrors and lenses, you can have them that go out or go in. If they go out, they're called convex. If they go in, they're called concave, which is easy because you can imagine it has a little cave. Okay, this would be a convex lens, and that would be a concave lens. So if you have this convex mirror, the light comes off of the image and then it reflects off this way, and it looks bigger. If it goes in like this, the light reflects off. So we got light reflecting that way, but it also reflects back here. And it'll look upside down and smaller. So you can draw a little pencil upside down. It's smaller. And we're going to do some experiments with that. Okay? So now, over here.
Put you on board.
Did you have a question?
Yeah,
What'd you
no,
say?
never.
Okay, so if you've got a tank of water, a fish tank, and you put a light in it, the light that comes up here can get out, and the light that goes here can get out. And the light that goes here does okay, but it gets bent. And as it goes this way, it gets bent. But if you hit it at exactly the right angle, going toward the surface of the water, the light will get bent back down into the water. That is called total internal reflection. And they use it to make fiber optic wires. Have you ever heard of fiber optics? It's where they make little glass or plastic wires where the light bounces inside of it and can't get out. And if that's probably how you get TV. Unless you have a dish on your house, then your TV comes as little bits of light shining through those wires. Okay? Feeling good so far? Okay, so now let's look at, can I scroll?
Not yet.
Not yet.
Oh, wait.
I didn't eat enough lunch. I'm hungry. And it's 1 o'clock. Not good. Okay, can I do it?
Yeah. No.
Yeah.
You can go.
Okay. All right, so we're going to talk about some things. These are pictures on the back of your notes. And these are things you're going to have to identify on the test. You'll be labeling it. So this is a model of how brightness of light looks. These are 2 spray cans. And they're both got the same pressure, same paint, everything, but this one's further back. So if we sprayed them together, the paint here would be less concentrated, where here it would be darker. That's what light does. The further you're away from a light source, the lighter it is because the light gets spread out more. Okay, next idea. Your eyeball. Okay, so this is what your eyeball is like. You're going to have to identify the parts of it on the test. First, you have the cornea, which is this little transparent thing over the center of your eye. And then you've got the colored part of your eye that goes here and there. It's called the iris, and it moves. It gets bigger and smaller to let more or less light in, depending on the situation. The hole where the light goes in is called the pupil. And it goes through this thing that's kind of like a glass lens, but it's not made out of glass. It's a lens that bends and focuses the light. Now, the cool thing about it is it's not rigid. See these little muscles here? They can pull on it and stretch it. It can get fatter and thinner depending on how thick it is, and that's how you can focus on something here and then look out there. As you get older, the lens gets more lens material on it every year, like a tree getting another ring, and it starts to get stiff. And that's why as you get older, you got these lovely little reading glasses, because my eyes won't go from here to there anymore. I have to use the glasses to focus. My eyes won't do it. Okay. Then you've got the back of your eye, which is called the retina. And on the back of your eyes, it's coated with what sees what sees. And there in the back here, in the middle, it is covered with cones that see color. And that's easy because cones and color both start with the letter C. And on the edges, you have rods that see black and white. And then in the very back, you have an optic nerve that takes all this information to your brain. And that's what causes your blind spot. Is there's a little spot right there with no rods or cones. So everybody try this. Look at your finger in front of your eyes.
I can't read it.
Look at your finger in front of your eyes. Okay? Notice how you can see the color of your finger really good, and you can see the detail. You can probably even see your fingerprint, can't you? Now, keep your eyes looking forward and go to the side. The color is less to see, and you can't see the detail anymore, right? It's because the cones in the middle see the color and the detail. The rods on the side see black and white and movement. Wiggle your fingers. Suddenly you can see them a lot better because your cones are picking up the movement. So that's why sometimes if you look directly at something, you can't see it as good if it's faint. But if you look a little to the side, you can see it better. So that's kind of interesting. Now let's go on. If I get this to the eyeball. Okay, so some of you have perfect vision. Disgusting. I wish I had perfect vision. Your eyeball is perfectly formed, and when the light comes through it, it is focused on the back of your eyeball, and you see perfectly with no glasses. Disgusting. Some of you have to have glasses or contact lenses. Okay, so we have nearsighted and farsighted. So what I have, I am nearsighted. So that means my eyeball is too squished flat this way. And the light coming in focuses before the back of my eyeball. And at the back of my eyeball, it's all fuzzy. If the back of my eyeball was here, I can see, but I can't. So I wear contacts, okay? And so they have to have a lens like this. You have to have a concave lens, see how it goes in, to focus the light on the back of my eyeball. Some of you are nearsighted, which means you can't see here, you have to wear reading glasses, but you can look way out there and see fine. I'm the other way. Without my contacts, I could see this great, but I could not see Brian. He would just look like a green blob back there. So some of you are farsighted, and that means when you're without your glasses, your light would focus way back here, back in your brain somewhere. And so you have to wear a convex lens, and then your light focuses right there on the back of your eyeball. Dalton, are you with us? Don't fall asleep. Okay, now this part you already know about. The electromagnetic spectrum. You already know about Roy G. Biv. You know about Ronald McDonald as extra gross. So this is just telling you the order that it's radio waves, then microwaves, then infrared, then visible, then X-ray, then ultraviolet. Oh, I did it wrong. Whoop, you didn't notice that? Doop, doop. Okay, let's try that again. Red. Okay. Visible, ultraviolet, X-rays, gamma rays. Ta-da! Everybody just draw your arrows there. We know about this, right? We studied it already in a couple of units. Everybody can draw those arrows. Okay, this shows you how light changes depending on what medium they go through. So this is light in empty space or a vacuum. It goes the same speed. Water, it slows down. Glass, it slows down more. Diamonds, it slows down more. And this is why it changes directions if we're going from one medium to another. Imagine this is a little car at your house. And this is the kitchen floor that's like tile or hardwood or something like that. And this is the den where it's carpeted. If your car hit like this wheel would slow down because it's on the carpet, but this wheel would keep going fast because it's on the tile, and that would turn it, and it would get bent. It would get refracted. And that's what happens with light. Take out your earbuds, put them in your book bag. Where's your book bag? Book bag in the cubby. My goodness, y'all are acting like this the first week and you don't know the rules. All right, let's go to the next one. All right, let's see what we're doing here. Okay, don't write until I talk about it, and then I'll let you talk. I'll let you write. Okay, so now we're going to talk about color. White light is made of all colors mixed together. Light reflected is what causes color. So like, where did I put it? Here I have this little pink dish. All the colors of light are being absorbed except pink, and pink is being reflected so you see the pink. So that's where color comes from. It's what is reflected. Light reflected causes color, and the color depends on the light and the object. Have you ever had something that looks one color in one light and you take it somewhere else and it looks another color? So the color depends on the object reflecting, but it also depends on the light. Luis, what are we doing? Get one over there. I think it would be wise for you not to get within the temptation of your phone that's in your hand. Bring it to me. I think your phone needs to be on my desk. Put it right here for the rest of the period for me. For real. For real. Right there. Right there. For real. I want to see your phone right there. Y'all are so addicted. Y'all are like little babies to your pacifier. Y'all cannot be away from your phone for a second. See, Luis was probably about to have a hive or a conniption because of his phone. And it's like a fit. He was about to have a fit because his phone was so many feet away from him for so long. Just that right here. We just gotta listen for just a little bit. Lay it down and you can do it. Be strong. Internal fortitude. You can do it. Quickly, Luis. Stop. Luis, look at me. You are interrupting my class. I can write you up for that. I don't want you to. I want you to sit down and pay attention. Be good.
She recorded. I forgot what it.
I am. Everybody in all of YouTube land, all my 800 subscribers are going to see that Luis was having a bad day.
How many viewers on like
Dang.
How many viewers I have? I've had over 70,000 views.
70,000.
Yep. All right, now let's talk about colored light. Colored light makes things look differently. If you shine a light on a red light on a green object, it will look dark. If you shine a red light on a red object, it looks red. And you can see that with colored cellophane, it acts like a filter. And the reason why is it only transmits the color of light that it is. So we're going to do some labs with filters, with colored light. So I'm going to do a lab where you go around to different stations, you get to see the slinky, you get to see the other things like that. But and some of them I'm going to kind of, I'm going to, where we'll do full out labs, but some of them we're just going around to stations. All right, do y'all have this? You may write it down now. Does everybody have it? So we can move on. And then here's our question. How would you describe the color red to someone who's blind? I don't think I could. I don't think I could do it.
Dark.
Dark. What is red? Dark.
red?
What is the essence of red? Blood? Strawberries? What is the essence of red? Is it happy? Is red happy? Angry?
Angry.
Angry, maybe. Red is angry. That fire ant looks kind of red and angry. But that red balloon looks happy. So I don't know. I don't think I can do it. All right, can I scroll now? May I?
Yeah.
Okay. Whoop. More phone sound effects. Okay, so here, there's just some things about that you already really know. I'm going to show you a prism. It's like a glass or plastic triangle. And if you put white light in, it splits it into the rainbow. The rainbow is Roy G. Biv. Since white light is made of all colors, it splits into the rainbow. So red has the least energy, violet has the most. And if you take colored light and mix it, you can get white. Okay. Now can we move on to paint? Not yet. But see, we already knew that, didn't we? So that's pretty good. Mama, no phone. Take out your earbuds.
It's
not on.
Yeah, I don't care. I want to see you go put them in your book bag.
It's not.
I don't care. Go put them in your book bag. Go put them in your book bag.
Oh, yeah. Go back. Look at it.
I want to watch you go walk to your book bag and put them in it. And then put your book bag in the cubby. Phone in the book bag in the cubby. Your cubby is number 4, I think.
Yes. My whole bag already in.
Okay, good. All right, can we scroll now? Didn't I do a good job drawing that eyeball? Are y'all impressed with my eyeball? Okay, can I scroll now? Okay, seeing color. We're going to start over here. Color facts. We already talked about this. The cones in the center of your retina sense color and details. The rods on the side sense light and black and white.
Brian got his beats on. It was loud. I can hear it.
Who does?
Why are you snitching, bro?
Who are we
Because we
snitching
all
on?
go fall under this boat if everybody can't listen to music. So.
Brian, take your headphones off. Brian, take your headphones off.
I can't even hear you.
I know, but he saw me.
Brian,
This is how I get so many viewers, because I wonder how this works.
Right. What happened?
I need your headphones, please. Because you're listening to them and not me. Thank you, sir. They're going to sit up here until time to go. They'll just stay right here. They're safe. Nobody's going to touch them. Okay. The cones see red, blue, and green. Isn't that interesting? The color codes see red, blue, and green, but your brain translates that into all the colors. The eyes blend the colors, purple, orange, etc. Colorblind are missing chemicals in the cones. Most mammals, animals don't see color. Bees can see UV but not red. They can see, so they see colors we don't see, but we can see a color they don't see.
So they colorblind?
They're not colorblind. They just see, bees see color different, but most animals are colorblind.
So like dogs, they colorblind?
Dogs, I think, are colorblind.
So
Yeah, they
dogs
don't see
can't
colors.
color?
I don't think they can. We'll have to Google it, but I'm pretty sure they can.
See certain colors.
They can see certain colors. Which ones can they see?
Their sight is very similar to red-green color blindness.
So they can see a little bit of color. I'm glad. I'm glad dogs don't live in a black and white world.
What?
Wait, go back up a little bit.
Oh,
I need to see red, blue, and yellow. What was it?
Oh yeah.
oops.
Wait. Sorry. I can't see.
There we go.
It's red, blue, and yellow right there.
Where did I put it? Right here.
It's like when you go over there.
You need to go up some more. Don't write these down yet. Just that.
Can you,
I'm gonna show you red,
what's it saying? Shut up.
Color and details, white, black, and
No,
white.
not that. I'm talking about the right side.
Red. We're not here yet. We're not doing that yet. We're not doing that
Fair
yet.
word.
Anybody else? Oh, I didn't print all of that.
It came that fast. It came the next day.
All right, let's finish these up.
It's like-
I'm ready to be done. Okay, can I talk about this? So you learned this in elementary school, that you can make all the colors of paint from red, blue, and color. Red, blue, and yellow. I've talked too long. Listen, y'all settle down. We're almost done. Red, blue, and yellow. But the background effects, and we're going to do a lab where you look at different colors, and it'll look different depending on the background. So paint is one thing. Ink in your eyes is something else. Ink is different. Ink, like when they print a picture of ink, not paint, then it's made with 4 colors: cyan, magenta, yellow, and black. And that's how they print pictures out of those 4 colors. And then this is how you blend them. Cyan and yellow make green. Yellow and magenta make orange. Magenta and cyan is purple. Cyan, yellow, and magenta is brown. So this is green, orange, purple, brown. But they can get all the colors just from those little dots of ink. And then your eyes help blend it and get all the colors. Your brain helps. Okay?
What's next to scattered?
Next to what?
Scattered.
Down there? We're not down there. Nothing. We're not scattering yet. All right, can I scroll? Oops, come on. Okay, why is the sky blue? The atmosphere has in it dust and water, which scatters light, especially blue and violet. So everything else gets scattered away, and what's left that you're seeing is the blue and the violet. So clouds look white, but with sunsets, you're seeing through more atmosphere. It's thicker because you're looking out. You're looking, instead of looking straight up, you're looking out, so you're seeing more gas atmosphere. And so that makes it where it scatters everything but the stuff at the beginning of Roy G. Biv, red, orange, you can see yellows and sunsets. Where the regular sky is the Biv part of Roy G. Biv, the sunset is the Roy. You see the Roy more. These colors are reflected from the clouds also, so that's why at sunset you see, there were really pretty pink clouds like night before last. Did y'all see them? They were just smooched across the sky. It looked fake. These little cotton candy pink clouds. Okay,
Wait, what's that say? Scatters all.
where are you?
The sunset.
Oh yes, the scatters all but red and orange. So it's all about which light gets scattered and what doesn't, so you can see it. Now, why are the lakes and oceans blue? Water absorbs light, but not all colors equally. Blue is the least absorbed.
Jalen, what you doing?
That's my mom.
On Instagram?
Why are we having this big phone fight today? Put it up here. Luisa's phone is lonely. Go put yours next to it. He needs a buddy. He needs a buddy phone.
Wait, what?
That's fine. Y'all are just interrupting class. Let's finish up. No. We already had that discussion. At the end of the notes, if we can ever get through them, you can go. If you have a pass. Do you have any passes left? Okay, well, we're getting there. We can do it. Focus. Okay, so blue is least absorbed, so that's why it looks blue. But sometimes the microbes can make the water look a different color. Have you ever been to White Oak Park and seen when the pond looks green? Because there's green stuff growing in it. You can even have red looking water from a red tide is called by microbes. Okay, can we go to the last page? Okay, so this is remember when we did our literacy activity for Bohr? And remember Bohr, who made the Bohr model, and Einstein would fight about dualism. Can something have two natures? And Einstein said no, and Bohr said yes, and Bohr was right. Because light has two natures. It's like a particle and like a wave. And it's like energy. So this is the evidence of light being energy. It's a lot like heat. You turn on your toaster, heat comes out, but also those little wires glow with light, don't they? And also it can be given off by chemical reactions like a glow stick. And it can be given off by electrical resistance. That's all like energy. Light causes change. Remember the Greek letter delta means change. And we can see that in photosynthesis. Light like energy turns into food. Film can be exposed by light. And chemical reactions can be controlled by light. You know, like when they do your teeth and they shine a light on it to fix your cavities or to make your teeth whiter. All of that is chemical reactions controlled by light. So light travels in two ways. Light energy can be carried or in waves. And like energy, it can go through empty space. So all of that is proof that light is like energy. And that's what we started off our lesson with, is that light is like energy. Okay, the next thing is that light is like a wave. So light acts like a wave. How does it act like a wave? It can be reflected like a wave. Ocean waves can bounce back, right? It can be refracted. It can bend off a different way like waves. And it can be diffracted. It can be dispersed like waves can. It can have interference like waves. And there was a famous scientist, Thomas Young, who did an experiment with that, showing dark and light lines, and that showed it's like a wave. He used some monochromatic one-color light. Another thing that shows that it's like a wave, have you ever been to the grocery store at the, I'll go back up. Have you ever been to the grocery store in the summer and it hasn't rained in a long time, and then it rains and you're walking through the parking lot and you see rainbow puddles? Have you seen the rainbow puddles? It's because of this. It's called thin film diffraction. Light goes down and some of the light bounces off the surface. Some bounces off the layer between oil and water, and then some of it could like even bounce off of the water, and that causes the rainbow. The oil splits the light into the rainbow, the color spectrum, and that is all light acting like a wave. Okay? And then the last idea is that light can be like a particle. Light can be like a particle. Can you come back in like 5 minutes? We are almost finished with the note. Yeah. 5 minutes. All right. So light can also be like a particle. And one reason why we have proof of that is when electrons hit metal, when light hits metal, electrons are released. So you can take light, shine it at metal, and it splashes out electrons. That's like a particle. It's got something to it. It can splash out electrons. Einstein came up with this idea of photons. They're light energy packets, and they act almost like little particles, these photons. They're a lot like an electron. Violet light has more energy than red, and that also is something that is a proof of it being a particle model. Another idea is that photons, these little packets of light, can move at light speed, and they can be absorbed and the energy converted. That says converted. It says converts. Energy converts. Okay, and then I'm going to tell you this last little bit, and then I'm going to not zoom out where y'all can finish writing them down. So there's a thing called polarizing filters, and it's where it only lets light through in one direction, and it's really great for sunglasses. You ever seen it on your sunglasses where it says polarizing? It cuts the glare, and we're going to do an experiment with that. I bought some to show you how they work. So polarizing filters light, and they're in sunglasses, and it cuts down on glare. Okay, so that's the end of the notes. I'm going to make this smaller again so y'all can see the whole page at once. And if you can't see it, take a picture and you can zoom in. All right, you've got over 15 minutes to work on your worksheets. Get them done, work with your lab partner, and you can not have any work to do tomorrow. You can go fishing. Go to the mall.
Go to the outside.
All right. Like, share, subscribe. Science is great.